Here's a bite from Newton's apple.
Recognize this image. Look carefully. It's a picture of Albert Einstein. The problem in recognizing this face is that to your eye, this picture is just a mass of dots. It's up to your brain to assemble these points into a recognizable face. This is just one example of how vision really occurs in our brains. And nowhere is this principle shown more successfully than at the Exploratorium in San Francisco. That's where we sent field reporter Peggy Knapp.
We're looking at an image of the Exploratorium in San Francisco through this special lens called a Fresnel lens. Now, the real object, the building itself, is actually behind me. The image is made when the lens gathers the light that's being reflected off of the Exploratorium. In fact, everything you see is really light. You could say that you're not seeing me, you're seeing the light reflected off of me. And it's easy to bend light into new patterns. That's why images can fool you. Images are also subject to interpretation by our brains. For everything we see, our brain plays a key role and provides any missing information. The vision exhibits here show how the eye and the brain work together. Sally Dunsing, the assistant director at the Exploratorium, was my guide. How do we see? How does the eye work?
Well, let's start with the lens.
All right.
Each of your eyes has a convex lens, kind of like this, and they take the light from the outside world and actually bend it and make an upside down or inverted image on the back of each eye.
But we don't see upside down.
No, and that's the point, because seeing isn't just in the eye, it's in the brain as well. So the brain, somewhere in the brain, the image gets reinverted, so you see a real image that's actually right side up.
The image on the back of our eye is not only upside down, it's also flat, distorted, full of holes, and out of focus. So our brain has to fill in the gaps. For example, this image is a miracle of eye-brain coordination. A thin wand waving in front of a slide projector reflects this picture to our eyes. Now we'll slow down the motion of the wand, and we can see that our retina is receiving only tiny slivers of the image at a time. Like a detective, it gathers clues from the patchy evidence our eye receives. Optical illusions can show us how our brain solves visual mysteries. Okay, Sally, what's going on here?
Well, this is a painting that's done in proper perspective, but the two curves aren't. They're actually the same size. And this is one way to show you how important size and distance cues are as you interpret what's going on.
They're the same size?
Yes. So stand over there and take a look.
All right, well, it still looks a little out of kilter, but this cow looks larger from here.
And what's happening there is you're actually closer to that lower cow's head, and it makes a bigger image on the back of your eye, so it kind of cancels out the illusion.
Oh, I see.
And now if you walk over to the left, now you're that much closer to this upper cow, and what does it look like?
It looks huge.
So the illusion is that much stronger because you're that much closer to this cow's head. Now you measure them.
Uh-huh. Well, they are.
You see, they're really the same size, and so now that you've seen it,
I still don't believe it. Our brains tell us that objects on the horizon are smaller. In this case, our brains are wrong. Do you see red, green, and blue stripes of color on this spinning wheel? Excellent. Your brain has just fooled you again.
Okay, now watch what happens. I'm going to turn it off, and you can see what it really is.
It's black and white. How does it do that?
Well, good question.
And the good answer is?
Nobody's quite sure. You need a wheel that's half black and half white, and on the white you need these black lines that kind of interrupt the white, and when it spins it creates like pulses of light that come to your eye. And for some reason your eye-brain system interprets those pulses as color.
I think I'm getting hypnotized. Sally, I've seen this exhibit and I know what's going on here, but I
still can't believe that my poor little brain is this easily fooled.
Well, what do you see?
Well, I
when you
see
look at it?
one white piece of paper with a tail down the middle.
And if you move the tail?
There's an edge there.
Yeah. Well, this is actually a really good demonstration of how important edges are for your eye to make a distinction between things that are lighter and darker.
But how can I be so easily fooled when those are so different in color?
Well, actually, there's another part to this illusion that enhances it.
I knew there had to be.
These two squares are identical, but
Yeah.
they're not uniform. So it gradually gets from light to dark. It's light on the left, and it gradually gets darker. So like at this edge right here, this gray right here is as dark as this gray over here.
Really?
So use this card here, and I'll hold the
that.
tail. And now look at those two grays.
I can prove it, but I can't figure it out.
Seeing isn't always believing. And nowhere is that more true than on the other side of the looking glass.
This is a great illusion that's caused by mirrors. And what this thing is we're looking at is a piece of glass that actually has a lot of silver in it, and so, or chrome. So it acts like a mirror, too. So I can see myself, but I can also see you on the other side.
So if we sit the same distance from this piece of glass, we're both inside the mirror and our faces blend.
Right.
Very weird.
Push the button. See what happens. Ah! It's half and half. Actually, we line up pretty good.
We line up pretty good.
Kinda
We're the
weird.
same person.
One brown eye and one blue, and this weird distorted mouth.
In learning about vision, we've come to understand that seeing really lies in the mind's eye.
Newton's apple is made possible by a grant from DuPont, makers of better things for better living, and also by this station and other public television stations.